Right, welcome back to our development of integration. So if we're reaching the hump really in many ways, I've called this particular workshop and the next part hump, and from there it's just consolidation. So if you can come to terms with the chain rule, practice, and do the work that you need to do, you won't get any surprises in Math 1. Alright, so I'm going to do a bit of a map here, just to help you see what goes on with integration. Now, we're not going to do a formal development of the theory of integration at this point. We'll have a look at that next week, but for this week I just want to jump straight in and start doing stuff, okay? So we're just going to jump straight in and just start doing stuff, okay? And just have a big old smile on our face. Just jump straight in and go whoosh, 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 and just have a lot of fun, okay? So, in the doing, there are a couple of techniques that we need, and they are colloquially referred to up and under. Now, all of this gets formalised, of course, and I'll do that as we go on, up and under. The next one is a log form, which is a substitution. Okay, a substitution. The next one is probably the most important thing next to chain rules in U substitution. So I'm going to be emphasising some things there for you. So I'm going to emphasise that. Okay, I'm going to put a bit of a line across here. We've got trig substitutions that get a bit more advanced. And then we've got things called partial fractions. And coming out of school, these are all the things that you would do if you did a complete extension 2, and then integration by parts. And not only that, you're going to learn all of these things in Maths 1. So Maths 1's got a lot in it. Okay, and I have talked about this in the intro video. So this is kind of like advanced maths, so mathematics. They used to call it advanced maths, but I'll just call it advanced maths. Mathematics now it's known as. This is extension 1 or the old 3 unit, and this is extension 2 or the 4 unit. So these guys here, this is a very hard subject. Really, to thrive in the Maths 1, you need extension 1 to do it really, really well, which means you've got to be a top student in advanced maths. So it's a lot of work. Getting here to uni and doing it up, you really should be proud of yourselves. Okay. Now, Maths 1 is going to be, all of this stuff is going to be assumed. They're going to want you to come in with this strong. Okay. And then when you hit this stuff here, you're going to need to recall and recognise and use all of the skills above that line. So it's assumed knowledge, and some of that's extension, but most of it is covered in the way that I deal with it. So you've got no real issues in terms of going into Maths 1. All right, so that's good. There's not that much we've got to do in foundation maths. In terms of integration per se, integration itself is meta. So this is like the meta knowledge about integration at university. It's studied on a number of different levels. So one of them is that there are improper integrals, and integrals that have a symbol, and the symbol has infinity on it, and various other things attached to it. So it's not infinity, so I'll change that. So we don't need to worry about those here. There's a subject called real analysis where you would deal with that. Okay. If you want to look under the hood, as it were, we're interested in proper integrals. Proper integrals are where we're headed, and so there's a couple of different ones that we're looking at. This week we're going to be looking at indefinite integrals. and indefinite ints have an expression and a big old capital C next to it. Okay, definite integrals result in a number. So we get two different types of outputs for a number, and it's usually an area, or it is an area, and example, meters squared, it could be centimeters squared, but millimeters squared, but it's usually meters in the practical problems. So there's a number of things that I could do now in terms of revising our diminishing triangles, but I'm just going to leave those and maybe come back to that. We'll see how we go. But essentially what we're going to do is jump straight in, and effectively that means that we're having a look at what's the relationship between differentiation and integration. Okay, and the answer is undo. They are inverse processes. Okay, they are undo. It's an inverse process, and the way that we think about the anti-differentiation is that it's an inverse. Okay, so we're used to taking a y and differentiating it. Y dash is equal to x squared. Now, I want you to think about what would it be like if we went in reverse. What if we were given y dash is equal to x3? x3, what would have to happen in order for us to go backwards? What would we differentiate to get x3? Well, we know, and this thing up here is called the antiderivative. No, it's not, it's y. Yeah, I know. But it's also called the antiderivative when you're looking at it from the derivative point of view. Okay, I get that. So, well, we would have to have some number come out the front and one off. So the number that we would need would be 4. 4, one off, would give us 3. But there's no number out the front here. So if this 4 is going to come out the front, it would have to cancel. So maybe we're doing x on 4. Let's try that. Let's differentiate that. 4 comes out the front. 4 minus 1. We already had a 4. Cancel. So the antiderivative of x3 is x4. Now the other thing, of course, is if we had some constant here, 6, 10, 12, it would disappear, wouldn't it? Gone, because the constant m is 0. So this has told us, this is a very typical way to do this as an introductory level, okay? This has told us that x cubed has an antiderivative family, not just one expression, but a whole bunch of them. C could be anything, capital C could be anything. So what we want to do is recognise that this is a process. And this is what this is doing. I don't like the way this is presented, but it's very typical in uni, so I'm going to leave it. What would we do to get 3x squared? Well, we'd have something with a cube. Oh, the 3 came out the front. And we're left with, oh, that's it there, look. 3 comes out the front. 1 off. There you go. 3 squared. So that's the antiderivative. And any constant will just disappear. Okay. So antiderivatives is a process of finding an integral. So y dash is all of these things. Y dash is all of these different things. In other words, what is the y? Okay. So this one's pretty obvious. 4 comes out the front. So that used to be x4. On differentiation, it goes that way. Okay. This one here, well, 6 is factors of, that used to be a 3, because it was plus 1, 2 plus 1 is 3. So that came out there, so that must have been 2x3. Let's differentiate that. 3 2s are 6, tick, x squared, tick, okay? And don't forget you can have a plus c. But this one here, that used to be a 5. Okay, so if it was a 5, 5 became a 4. Okay, 4 plus 1, and then 4 was multiplied by something to give us 10. 5 was multiplied by something to give us 10. So that must have been 2. 2 5s are 10, and take 1 off. Okay, what about this one? Oh, well, it would have been 1. 1 comes out the front, so it would have been 10x plus c, going that direction. So these are interesting, to say the least. Okay, but what's the patterning there? We're going up, we're going up, up. 3 becomes 4. 3 becomes 4. 2 becomes 3. 4 becomes 5. X to the 0 becomes x to the 1. X to the 0 becomes x to the 1. Remember, that's 10 times 1. That's 10 times x to the 0. 0 became 1. And the same for this one. Okay, x to the 1. So it's up, up, and under. So let's have a think about it. Let's say we've got a differential. Plus some constant. Remember that the constant is multiplied by x to the 0, constant times 1. So that's what that mathsy eye is seeing there. Okay. Now let's integrate it. Let's do what we did up here, but integrate it. So what would we do? Well, we integrate both sides. You'll see this come up quite a bit. If this is an inverse operation, undo. If I'm integrating a dash, I'm going to end up with y. So that's an important piece of meta knowledge. Okay, I'll let you drink that in. And then we go along here and integrate both sides with respect to x. We'll talk about what the dx is next week. Up and under. So we're going to add 1 and divide by 3 plus 1. Okay. C is xo plus 1 divided by 0 plus 1. Okay. Then we're going to say plus a big C. Okay, so all of that translates to 4 over 4, so they will cancel. X to the 4 plus Cx plus a big C. C's are constants, remember. That's just 1. So this becomes y is equal to x for some constant x plus c. So that was our y dash. This is our y. So this is the formal process that we'll go through. We'll do the formal process next week, but for now we're just going to keep it informal. All right, so quasi formality. Okay. If x, I did this with you before a couple of weeks ago as code 2. Okay, if you recall, if you want to go back and watch that video, I did it as code 2, and it said add the power, so that was the algorithm, divide by the coefficient of the new power. Okay, or that should say the actual power. All right, so let's think about it for a minute. If I've got y equals x to the n, integration means that we use the sum symbol over many small increments of the sum. We'll get to that next week. And that equals add 1 to the index and divide by that new index. And don't forget your big C. Okay, so that there represents in words everything that's written there. And so we'll come to a more formal arrangement next time. So we've got a couple of things that we can do. So x squared, integrate x squared plus 2x. Let's put the dx in because even though we don't know the sum of the dx yet, what we'll do is up and under on each term. So you just treat each term like we were doing our differentials. Sometimes it's called the integral, the integrand. I is equal to up and under. One plus one divided by 1 plus 1. Don't forget our constant. Okay, so that means our integrand is equal to x3 over 3, 2x 2 over 2 plus c, so they will cancel. So our final integrand is x cubed over 3 plus x2 plus big C. Okay, that's our final integration. Very straightforward, up and under. It's the opposite of what we do for differentiation. So if we're integrating this one here, we might do a bit of pre-work. So put all of those industry skills and gymnastics together, and now we'll integrate the new form, and like we do in differentiation, we'll go along and term by term we'll apply our new rule. Okay, so term by term, and it's with respect to x, so we'll put the x. So 5x7 means up and under. 5x 7 plus 1 is 8 divided by 8. So we've integrated the first term. Minus 9x half plus 1 is 3 on 2. Divide by 3 on 2. Now your training has gone some way to deal with that. Okay, divide by 3 on 2 is the same as times by 2 on 3. Okay, and then this one here, 7 minus 2 plus 1. Minus 2 plus 1. So we end up with minus 1 divided by minus 1. So we just got to be careful of those nuances. Okay? So we get 5 plus c, don't forget your big C. So we've got 5x 8 on 8. Now that flips, so it's 2 minus 2 thirds 9, and that's the square root of x cubed. That will cancel, and so we've got a 3 by 2 product of 6. So we'll do that in the new line. Now this is minus, because that minus is going to take over the plus. There's 7 on the top, and the x to the minus 1 means it goes down the bottom. So our final little thing is 5x 8 over 8. 2 3s are 6. Minus 7 on x plus c. So that's your final answer for integration, up and under. Okay? So what we look to do is use these informal rules without the knowledge that we need, just to practice doing our parts, and that's all we're going to do today. Okay, we'll practice doing our parts, and so this formalises that. So when we integrate our function with respect to dx, we will end up with a result, a function. Often you'll see that. okay, plus some capital C, must have. If that's left off, wrong. Okay, and I'll just point this out. The differential of this is the function itself. Okay, so that's like the inverse operation happening. That's undo. Okay, undo. Okay, so for each of these, what we've got is where n's not -1. Now, what's this mean? Integral of a blank. Well, integral of a blank is the integral of the number 1. The integral of the number 1 with respect to x is x to the power 0 dx. Doing the integral would be 1 over 1 plus c, so we would get x plus c. So this conjured the variable. Okay, it conjured the variable, hence x plus c. We can take the c's out through the sign, and we can treat functions as individual integrals if we want to. Okay, so this one here, if we were to integrate x squared plus the square root of x dx, we could view that as the integral of x squared dx plus the integral of the square root of x dx. Okay, we could do it that way, and sometimes simplifying that does help, actually. All right, we'll pause there. We'll come back and do some examples, and I'll see you soon.